Namaste and welcome to this lecture on linear algebra through geometry. In the last lecture we looked at the homogeneous system of equations. Basically we looked at three equations, three unknowns and we looked at geometry of the solutions to the system of three linear equations and three unknowns. We saw how the zero vector or what do you call, or a vector which is perpendicular to a plane, or a plane, a set of vectors in a plane which is orthogonal to a given vector forms the solution space for AU is equal to 0. Now in this lecture what we will do is we will look at the idea of Gauss elimination again, but from the perspective of doing this LU decomposition, where you factorize this matrix or decompose this matrix in A, the square matrix A, the 3 by 3 matrix, into a product of a lower triangular matrix and an upper triangular matrix. Again we are going to look at this in terms of geometry. We will find out what is it to look at those elementary row operations which we did when we did system of equations. How does that translate to vector operations here, or what kind of vector operations that we do, and how the series of transformations that we are going to do is going to cumulatively become a lower triangular matrix, and those things is what we will cover here. And in addition to that we will also look at the idea of least square solution when Ax is equal to B does not have a solution at all. Like that corresponds to the case of parallel lines in 2D, and this could correspond to, let us say, skew lines, it could correspond to planes where they do not intersect. That is the kind of thing that we are looking at. So this will be the agenda for this lecture. Okay, so let us go ahead. So what are we going to do? We are going to look at the idea of LU decomposition. Now you may recall that the Gauss elimination that we did before, Gauss elimination has two parts, namely Gauss elimination has two parts. The first part is transforming the system, the system matrix A, the coefficient matrix A, the coefficient matrix A to an upper triangular matrix upper triangular form with forward elimination, and then to find the solution we did back substitution. Essentially what we did was the following: we had a system of equation, let us say Ax is equal to B. So we basically had this A11 x1 plus A12 x2 plus A13 x3 is equal to B1, A21 x1 plus A22 x2 plus A23 x3 is equal to B2, A31 x1 plus A32 x2 plus A33 x3 is equal to B3. This is the system of equations that we had, and when we had this coefficient matrix we had this to be A11, A12, A13, A21, A22, A23, A31, A32, A33, we had this into let us say x1, x2, x3 is equal to B1, B2, B3. This is what we had. Now, when we get to the row echelon form, we basically ensured that when we moved from this matrix A, when we applied elementary row transformation, applying elementary row transformations, it could be of a combination of those three types that we had, where we had row swap, replacing a row with one of the multiples of the same row, or replacing a row with the row plus a scalar multiple of another row. So, one or more of these elementary row operations that we could do in order to get to the row echelon form. So, applying elementary transformations, elementary row transformations, we get to the augmented matrix, let us say A B, we had this, the first row of A was retained as such, we had A11, A12, A13. Similarly, B1 was also retained as such. Then we ended up getting this, the second row first element was 0, we ended up getting let us say A22 star, which is basically after the transformation that we have done. Then we have A23 star is equal to let us say B2 star, and then we did 0 0, we had A33 star, which was equal to let us say B3 star. That is what we had, and this basically became Ux is equal to let us say B star, where B star is nothing but this column vector B1, B2 star and B3 star. This is what we had, right. It is interesting that we had this matrix A which was which is like this, and from this matrix we ended up in this upper triangular matrix. That means, if you actually do a column by a column to column comparison of this matrix A with that of U, we can actually see that, okay, let me rewrite this matrix A here for convenience. We had A11, A12, A13, A21, A22, A23, A31, A32, A33, and we have this matrix U on the other hand, which was basically this A11, A12, A13, and we had 0, A22 star, which is basically after the series of operations that you do, we have A23 star, then we had 0, 0, A33 star. Similarly, we had the original B matrix was B1, B2, B3, and the what do you call, after application of the elementary row transformations, we end up getting this B star matrix, which is basically B1, B2 star and B3 star. Basically, you apply a series of these elementary row transformations. Now, if you do a column to column comparison, it is very interesting to see that what was a vector of this form, a vector in 3D which was A11, which had components A11, A21, A31. Our series of elementary transformations, elementary row transformations that we did, basically transform this vector A11, A21, A31 to a vector which is just along the first axis, which is A11, 0, 0. That means, this vector A11, 0, 0 is basically along the E1 axis itself, right. Similarly, if you look at the second vector that we had, which is A12, A22, A32, that vector upon the elementary row transformation, the series of elementary row transformations that we did, basically got transformed to a vector which is just there in the E1 E2 plane, and the third vector that we had, which was A13 A23 A33, got transformed to another vector in 3D space, which is basically A13 A23 star A33 star. So, essentially what we see is when we apply the series of elementary row transformations, these are transformations applied on the vectors, column vectors, such that you get a structure like this. Therefore, what we want is we want to look at this B vector or the B star vector that we have here, which is basically B1 B2 star B3 star, that now we want to look at whether we can write this B star vector as a linear combination of these three vectors which are there in this U matrix. This is basically my U matrix and that is basically my A matrix. I am sorry, this is the matrix, this is the matrix A, this is the matrix A, and that is the matrix U. So, where have we gone? We have come from the matrix A to the matrix U through the series of elementary row operations. Now, what does that mean? Say for example, I may have this matrix, I have this matrix A, I have this matrix A to which I apply the first elementary row operation, which is nothing but E1, where, so let me write this, let EI, let EI denote the ith elementary row transformation, let me say ith elementary row transformation. I mean, it does not mean that I am operating it on the ith row. What it says is if I say E2, it is the second elementary row transformation that I am trying to do. Is that clear? E1 corresponds to the first elementary row transformation, E2 is the second elementary row transformation, and so on. I corresponds to the kith elementary row transformation. Is that clear? Transformation. So, what do we get? We basically have the following. We have the matrix A, upon which we first apply this transformation, let us say E1, and then we applied another transformation which is E2. Third, we applied another transformation E3, and we went on to apply a series of operations like this, and finally we had, let us say, En minus 1. I applied the n minus 1th row element row transformation, and I ended up getting, let us say, this matrix, the upper triangle matrix U. Is that clear? So, we did a series of operations and then I ended up getting this upper triangular matrix, which is U. Now, what is interesting is all these matrices that we do, E1, E2, En minus 1, each of these matrix will actually correspond to some kind of, if you look at the product of all this matrix, that will give a lower triangular matrix. Let us take a simple case. Say for example, I have this matrix A, let us say, which is, let us say A1, A2, A3, B1, B2, B3, C1, C2, C3. I have this. I want to go from here to a matrix U, which is an upper triangular matrix. So, what are the series of steps that I need to do to go there? So, if you see, my first thing is I want to make this B1 to be the 0 element, that will be 0, but that has to be made 0 because I have to get the first column, which is basically a vector which is along the first axis. So, I have to get that to 0. So, what do? I basically say R2 is nothing but R2 minus B1 by A1 times R1, and the condition is that A1 is not equal to 0. Yeah, and therefore, what do I get? I basically get E1. E1 is basically replacing the identity matrix with the transformation that we are going to do, which is basically 1 0 0. The second row has to be changed. So, the second row is going to be minus B1 by A1 times the first row, and the second row is retained as such 0. Then I am going to get 0 0 1. If I apply this on the matrix A, I will actually get A1, A2, A3, second component will become 0, second row first component becomes 0, second row second component basically becomes, it says minus B1 by A1 times the first row of the matrix A. You always remember this A matrix is sitting here, A matrix is sitting here. I am applying this on the A matrix. For the space constraint I have actually removed this. So, I have this, my third row is going to remain the same, which is nothing but C1, C2, C3 and so on, whereas the second row, if you actually see, second row is nothing but B2 minus B1 by A1 into A2, and this is going to be B3 minus B1 by A1 into A3, right. This is what we are going to have. Now, once we get to this matrix, what are we going to do? I want to make this particular coordinate 0, we know how to do that. You basically do another elementary row operation where you say R3 tends to R3 minus C1 by A1 times R1. Again A1 is not equal to 0, that is something which we maintain because divide by 0 will be a problem. So, what do I get? I will do 1 minus 1, this is going to be 0, okay, 1 0 0, the first row is same, the second row is going to retain as such, the third row is going to be minus C1 by A1 0 1, this is R3 minus C1 by A1 into R1, and where am I going to apply this to? I am going to apply this to the already transformed matrix which is obtained by this elementary row transformation E1. So, it is going to be minus B1 by A1 1 0 0 0 1 applied on A, which is A1 A2 A3 B1 B2 B3 C1 C2 C3. Yeah, I am going to apply it on this. Now, if you keep doing this and then try to make this element 0, you actually get into the upper triangular matrix, and when you do the upper triangular matrix, you would have actually done 1 2, there are 3 elementary row transformations that you have done, and if you look at the product of these 3 elementary row transformations, you will basically get a matrix which is the lower triangular, which is basically a lower triangular matrix L, right. So, what are we going to do here? So, what we are going to do? We are going to say that E1, we go back to the same thing, we say that E n minus 1, first of all I apply E1, E2, then I apply E n minus 1 on the matrix A to get this matrix U, which is U is upper triangular matrix, U is upper triangular matrix. Right. Therefore, now I can write the matrix A as the last transformation that I have applied is basically E n minus 1, and we must know that all these elementary row transformations that we have applied, we had seen even in 2D where we did row swapping and then shear and then scaling, all these were invertible operations. Therefore, each of these elementary row operations that we have done, E1, E2, E n minus 1, they are all invertible. Therefore, what I do? I am going to write this as E n minus 1 inverse, etc. It goes E2 inverse, E1 inverse into U. Now, if we look at this matrix, the product of this inverses of this matrix, we basically end up getting this lower triangular matrix L. So, we have A is equal to LU, where L is lower triangular matrix. Right? We have this lower triangular matrix. Now, what is interesting is we go back and then look at this elementary row transformation that we have done here. Where is that? This place. Let us just have a look at this. This transformation that we had here was applied on to the matrix A. Matrix A had 3 columns, that means this transformation is going to be applied on all the 3 column vectors that we have here. And if you look at this operation that we have done, it is basically some kind of a shear that happens along the x2 axis. Similarly, if you look at this, this is going to be some kind of shear which is happening in the E3 axis. Essentially what we are trying to do is we are going to use a sequence of shears and then scaling and then a reflection operation in order to get the rho echelon form, and that is exactly what our LU decomposition does. Is that clear? So, LU decomposition, precisely if you see, these are basically LU decomposition essentially is, if you want to go from the matrix A to the upper triangular matrix, you see you apply a series of these elementary transformations which correspond to one or more of the three types that we have had: row swapping, scaling and shear. Apply that, you end up getting an upper triangular matrix. And if you take the inverses sequentially, we end up getting a lower triangular matrix, which means A is equal to LU. Now, why do we even want to look at this? So, we had AX is equal to B. Now, what is A? A is basically LU times X is equal to B, because we have done the decomposition LU decomposition of A. We have LU X is equal to B. Now, what you do, Ux is nothing but a matrix transformation. Again, Ux we can take Ux to be equal to, let us say, some y. So, what do I have, which implies Ly is equal to B. Now, Ly is equal to B, if you look at the structure of this system of equation, I am going to have something like this, a non-zero element here. These two guys are going to be 0. I am going to have two non-zero elements here, this is going to be 0. I am going to have all these three non-zero elements. So, you are going to basically get the lower triangular matrix into, let us say, y1, y2, y3 is equal to b1, b2, b3. So, what have we done here? We are going to collect we are going to identify the values of y1, y2, y3 in a forward manner. The first equation is going to give the first value y1, substitute that in the second equation, you get the value of y2, and substitute that in the third equation, you get the value of, substitute y1, y2 values, you get the value of y3. So, you are going to do some kind of a forward substitution here to get the values of, we are going to get the values of y1, y2, y3. Now, once this is done, we know the value of y1, y2, y3. What are we going to do? We know that ux is equal to y. This is going to be of the form, let us say u11, u12, u13, 0, u22, u23, 0, 0, u33, and what is that? We have x1, x2, x3, and we end up getting this y1, y2, y3. So, what we do? We basically do the backward substitution and get the values of x1, x2, x3. So, ultimately what we see is we are trying to apply these the transformations on the vectors, basically all this kind of linear transformations on the vectors, column vectors, and then to basically get the scalars x1, x2, x3. That is precisely the idea of your Gauss elimination also. And one of the ways that we try to do is we basically try to decompose the matrix A to be equal to a product of a lower triangular matrix and an upper triangular matrix to get the value of x1, x2, x3. So, solving for x1 and x2, x3. So, we basically get the value, let me write this. So, we basically get the values of, we get the values of x1, x2, x3 by back substitution. Okay. Now, this is all fine. You have actually a computation algorithms which will help you get this. In fact, an easy way to look at it is of this form, and in case of LU decomposition, the diagonal elements must all be 1. If you have this L, these diagonal elements must all be 1, So, that is what we are looking at. So, an easy way to look at this is basically doing this. So, understanding LU decomposition, we can get this. I am just doing it for a 3 by 3 matrix. I mean, one can get it for any n by n matrix. Of course, the I mean, the thing is, like, since your what would you call your L matrices, the set of elementary matrices that you have, they are all invertible. We will also look for we also have this matrix A to be an invertible matrix. Okay. Now, so let us look at how do we understand this LU decomposition. So, let us basically take it this way. I have my column, my A matrix A11, A12, A13. We have A21, A22, A23, A31, A32, A33. I have my lower triangular matrix, which is basically 1 0 0. I have L21, 1 0, L31, L32 and 1. Similarly, I have the upper triangular matrix, which is basically U11 0 0. I have U12, U22 0 and U13. Let me write it corresponding to the column. So, we will write U13, U23, U33. This is what we have here. Let me rewrite this. So, you have U12, U22, 0. This is what we have, and if you actually see it very clearly, there is something interesting that we can make out here. We see that we are basically given the value of Aij. So, given Aij, we need to find out Lij and Uij, right. So, how do we do this? We see very clearly from the previous page, we see this, we can write this matrix A as a product of L and U. Let us try to get it clearly. So, what we have? We have the elements of A, below the diagonal. That means we are going to look at this A21, A31 and A32. If you look at that, we can write this as can be written as Aij is equal to Li comma 1 U1 comma j plus etcetera plus Li comma j minus 1 Uj minus 1 comma j plus, these are all subscripts, Uj minus 1 comma j plus Lij Ujj, and what we are going to say is this is for basically j less than I. And we can actually see very clearly that the elements of A that are on or above the diagonal, we have the following. It says Aij is equal to Li1 u1 comma j plus etc. Li I minus 1 u I minus 1 comma j plus Lij u I j. This is u I j for j greater than or equal to I. So, in a sense, how are we going to get the values of Lij and Uij? We are going to see this, which implies Lij is equal to 1 by Ujj into Aij minus Li comma 1 u1 comma j minus etc. minus Lij minus 1 uj minus 1 comma j, and this is basically for j less than I, and we are going to have uij is equal to Aij minus Li comma 1 u1 comma j minus etc. minus Li comma I minus 1 u I minus 1 comma j. This is for j greater than or equal to I. That means you have actually got the values of the lower triangular matrix and the upper triangular matrix, the Lij values and Uij values, right. And that is the way we that is exactly how we end up getting the elements of Li, I mean the lower triangular matrix and the upper triangular matrix. And of course, when we need pivoting, we can always look at the idea of permutation matrix. That means you can do this row swap and stuff. In fact, what is interesting is you can actually do a series of shear transformation and still get and end up getting an upper triangular matrix. Even that is possible, right. So, having done all these things, what we do is in today's class we in this lecture we basically looked at the idea of LU decomposition. We applied a series of linear transformations, those 3 linear transformations corresponding to scaling, reflection and shear on the vectors, on the column vectors of the matrix A, to get an upper triangular matrix which basically had the columns to be in the following manner. The first column was the vector which is a vector along the first axis. We had the second column of the upper triangular matrix to be a vector in the plane, I mean you can say that it is there in the x and x2 plane, and the third vector is going to be in the 3D space. So, that is what we had. And then what we did is, like these series of transformations that we applied on A to get the U matrix, each of those operations that each of those transformations that we did, they are all invertible, and therefore you did the inverse of it. So, from A we went to U, we can always go from U to A by applying the inverses of the transformations in the reverse order, and that is exactly how we got into the idea of A is equal to LU, that is this LU decomposition, which is typically the which is typically what we use in Gauss elimination. I mean in the sense we convert this matrix A to an upper triangular matrix and then do the back substitution. First of all, forward elimination and then you did a back substitution, that is your Gauss elimination in order to find out the solution to Ax equal to B. Now, the question is, we may not have a solution x at all to Ax equal to B. Where did we face this situation? When we had 2 parallel lines in 2D, there was no way that we could get a value of x1 and x2 which satisfy both the equations simultaneously. And in 3D also we studied the idea of skewed lines, which means the lines are I mean they will never intersect and you do not have a solution. So, in which case, I mean what do we do with the system of equations? Can we say that we do not have a solution to the system of equations and leave it as such? But that is not what we look for. So, what we do is we want to find out what is known as an approximate solution. That means the right hand side is something, we will try to approximate the right hand side with something else, and for that approximation we will find out the value of x. That means there is going to be an error between what is given as the original right hand side and what is the right hand side that we use as the approximation, and the idea is to minimize the squared error between these two guys, and that is exactly where we get into the idea of least squared solutions. We will look at the idea of least squared solutions followed by the Gram-Schmidt orthonormalization process, and of course we have done inner product. We will just spend a little small time on the inner product. We will look at Gram-Schmidt orthonormalization in order to get orthonormal vectors, which are basically in order to find local coordinate system with orthonormal vectors, and after that what we will do is we will look at yet another decomposition of a matrix A, which we call as the QR decomposition, which is actually which you can obtain from the Gram-Schmidt orthonormalization process, and that will be the next decomposition of the matrix A that we will be seeing. Once that is done, we are getting into the idea of a general linear vector spaces, where we are going to formally define the idea of vector spaces and linear independence in the vector spaces, bases, subspaces, dimension. We are going to look at a lot of other important terms and important ideas associated with vector spaces, and we will combine whatever knowledge that we have gathered till now with the knowledge of vector spaces and see we will try to see the if you remember, like we in the introduction to the course we said that linear algebra is basically a very beautiful interplay between algebra and geometry, and we need to make that connect between algebra and geometry, like from system of equations to the vector spaces idea. We will do that once we define vector spaces, subspaces and all those things. So, we will do side by side the system of equations and the vector spaces, and we will do this connect between these two guys so that we understand better. So, we will look at it in terms of again system of equations, and we will do it in terms of general geometry. Whatever ideas we have gathered here, we are going to employ it in further lectures. So, let us meet for the next lecture on least squared solutions and Gram-Schmidt orthonormalization process, followed by QR decomposition. Thank you.